Hello everyone, Mr. Tomasic here. Today I want to talk to you about pressure. What is pressure? First, let's take a look at some vocabulary. First, let's just define gas pressure. Gas pressure is the result of simultaneous collisions of gas particles with the surroundings. Now, remember when we talked about KMT, kinetic molecular theory, and all stuff, solid, liquids, or gases, are made of little particles that are flying around. And when these particles hit stuff, like the floor, the ceiling, the walls, they push on it. They push on it. Now, they're invisible, so you don't really see anything. And the pressure that you feel, you don't really notice because on the outside of your body, the pressure is the same as on the inside of your body. All right? It's those differences in pressure that you would end up feeling, and the gas pressure when it hits stuff is from the molecules hitting things. Now, if we had some kind of a container, like say a test tube or something like that, and we were to suck all the air out of it, there would be nothing inside, and therefore there would be no air pressure inside. We call that a vacuum. Now, it's very difficult to actually create a perfect vacuum, but we can get the pressure really, really low on the inside of some things, and we call it a vacuum. And if you ever heard the term vacuum cleaner, that's exactly what happens. You have this container, and you have a fan that sucks the air out of the container, and it creates a vacuum. And then you open up a hole that's close to the ground, and then dust and dirt goes flying into the vacuum. It's a vacuum cleaner. Now, when we talk about atmospheric pressure, we're talking about pressure from the air that's around us. Now, we could have a container like this container of propane, and inside of it has a pressure, and it might be greater than the air pressure on the outside. If I open up the valve, then the gas can come flying out. All right, so the pressure on the outside would be what we call atmospheric pressure. It's the pressure from the air hitting it. So the air inside here may be more or less than the pressure on the outside of it. Now, how do we measure pressure? We use a device called a barometer. All right, a device called a barometer. It's a thing that measures pressure. Now, meteorologists, weather people, they use barometers all the time to measure the air pressure, because when the air pressure goes up and down, it can tell us something about what's going to happen with the weather. When the pressure is rising, generally we got good weather. When the pressure is falling, that might indicate bad weather is rolling in. All right, when you have a hurricane, and nowadays hurricanes are kind of big deals, it's a swirling huge mass of air that's low pressure, and everything moves into the middle of it, and as it moves in, it spins around and creates a tornado. So at the center of a hurricane is a very, very low pressure system, and if the pressure is so low, it makes wind, very, very strong winds. All right, so air is all moving in toward the center of a hurricane because the air pressure there is low. And when it moves across the surface of the earth is moving, spinning, so it makes the air spin too as well. That's why tornadoes and hurricanes actually spin. All right, so we'll be using these terms a little bit as we go here. Now, because pressure is the result of molecules hitting things, we could talk about fluid pressure, or we could talk about air pressure. Now, you've experienced changes in pressure a lot. For example, most of you probably have dove down into a pool, say on the deep end, and gone about 6-7 feet below the water, and quickly you realize that there's higher pressure when you go down deep. It pushes in on your ears, and it kind of hurts. In the case of swimming, though, once you go down about 10 or 12 feet or something, the pressure gets so intense on your ears that it could actually destroy your eardrums. Now, to prevent that from happening, people have the ability to allow water to enter inside of their head, go past their eardrum. So that prevents your eardrum from getting destroyed. All right, if you didn't have that ability to let water go inside your ear, the increased pressure would literally destroy your eardrum. And that's why when you go diving down under the water for a little while and then you come back out, you got water in your ear, because your ears are trying to equalize pressure to avoid damage. All right. Now, people that go scuba diving, that is, go way down in the water, they learn how to do this very quickly. Allow their ears to adjust, and the further you go, the more you have to allow your ears to adjust in pressure. Now, because water is so much more dense than air, going a small distance down into water creates a huge difference in pressure. The deeper you go, the higher the pressure. Whereas in the case of air, air is much less dense than water. So as you move, you have to go longer distances to feel differences in air pressure. Now, most of you probably, or some of you have been in airplanes before, and when you fly up into an airplane, you realize that sometimes your ears pop. All right, why is that? That's because when you go up in altitude, the air gets thinner and thinner, and the pressure gets less and less. And when you're on the ground, the pressure inside your ear and outside your ear are the same. But as you go higher and higher, the pressure on the inside of your ear stays the same, but the pressure outside of your ear gets less, and your eardrums kind of bulge out. This can be kind of irritating on your eardrums, and because your eardrums are bulging out, they don't move as well, and it makes hearing a little bit more difficult. And then after a while, all of a sudden, boom, your ears will pop, and air will move from the inside, from the inside to the outside, and then they will equalize, and then they'll go back to normal, and then you can hear once again. When you come back down in the airplane, then the opposite happens. You're starting to go from where the air pressure is low at high altitudes down to ground level, or again where the air pressure is higher, and now your eardrums will sort of bulge in, and the same thing happens. And then at some point, your ear pressure, the pressure will equalize, and then you can hear normal again. All right, so changes in air pressure, even going up in an elevator 4 or 5 stories in a building, can change air pressure in your ears so much that you can actually sense it as well. Now, if you go up to very high altitudes, like 39,000 feet where airplanes fly, the cabin of the airplane has to actually be pressurized. All right, if you were at that altitude, you wouldn't be able to stand the low pressure. All right, the pressure's so low you wouldn't even be able to breathe. There's not enough air at that altitude. So they have to pressurize the cabin of the airplane and pump it up to try to keep it fairly close to what the pressure is at ground level. All right, otherwise your ears would pop really, really bad, and you wouldn't be able to breathe just because their air is so thin at that altitude. Now, where is the highest spot on the Earth? All right, the highest spot on the Earth, of course, is going to be at the top of a mountain. The highest spot on the Earth is Mount Everest. Mount Everest. And that gets up to, I forget what it is, almost 30,000 feet above sea level. All right, now sea level is the level of the ocean. So when you go on land up toward the mountains, you get higher and higher and higher, and the air gets thinner and thinner and thinner, and the pressure gets smaller and smaller. All right, so if you were at the top of Mount Everest, the air would be so thin, mountain climbers often will have to bring their own air. They'll bring little tanks of air because there's so little air up there that for that last 5,000 feet of going up there, most people have very difficult time actually breathing. Now, the opposite would be true at the lowest spot on the Earth, and there's a spot in the Middle East around the Dead Sea that is the lowest spot. Now, this over here is the Mediterranean Sea. It's at sea level, and as you go inward, you start to go downhill, and this is like kind of a valley here where the Dead Sea is. The sea used to be a little bit bigger, but over the many centuries it's sort of drying up. But that right there is the lowest spot on the Earth. And when you go there, the air pressure is much higher than it is anywhere else, and it's a little thicker. And sometimes people go there because it helps them to breathe better too, as well. All right. Now, what's the altitude where we are? Minnesota is right around 889 feet. All right, we're in Minnetonka. That's where we are, above sea level. And as you go closer and closer to the ocean, you start to go downhill, essentially. And that's why rivers flow to the ocean because they start where the altitude is high and then they flow their way down to sea level. So all rivers flow into the ocean somewhere. Some of you have maybe been up to Lake Itasca, where the Mississippi starts. All right, look at this map here. Here's a map of the Mississippi that starts in Minnesota and goes all the way to the Gulf of Mexico. All these other rivers flow into it, and it dumps itself down in New Orleans into the ocean. Now, all of this is downhill. So starting at the highest spot is where the Mississippi starts, and that's around Lake Itasca. Some of you maybe have been there. All right, looking at it, this is what it looks like. It's just a little creek, basically, and that's the start of the Mississippi. And then you go a little ways into the woods, and it sort of disappears into swampland, and gets a little bit bigger. There's the sign right next to this starting spot here, and you can read what it says right there. It says that you're at 1,475 feet above sea level, and then the river flows downhill all the way some 2,500 miles until it dumps into the Gulf of Mexico. And as it goes down through Minnesota and then Iowa and so on, lots of different rivers add into it. So by the time it gets down to the Gulf of Mexico, it's a very large river. All right, here's New Orleans, and the river's so big that huge ships can go in it. Whereas up there in Minnesota, it's just a little tiny creek that comes out of a lake. Now, so in Minnesota, it's at high altitude, and then it flows downhill. So we have that definition of pressure that results from air molecules or water molecules bouncing off of stuff and pushing on it. All right, now if we put a little bit of physics to it, in physics a push is called a force, a push or a pull. So if we take a push and we kind of spread it out over an area, that's how we actually measure pressure. It's force divided by area. And in physics we measure force in a unit called newtons, and we measure area in a unit of meters squared, and we give a special name to Newton per meter squared. We call it a Pascal, and we can abbreviate that with a PA. And we'd measure force in newtons and area in meters. So a Pascal is 1 Newton per meter squared. Now, in chemistry, we do use pascals, but there are other units too as well. All right. Now, this right here is supposed to be an illustration of the Earth, and say here's a little person standing here, and then all around the person is the air molecules. And because of gravity, the molecules are pulled down closer to the Earth. So as you get closer to the Earth, there's a lot more air molecules, and therefore there's a lot more air pressure. So we could measure that in Pascal, or we could measure it in a unit called atmospheres, because it's atmospheric pressure. So 1 atmosphere is the pressure at sea level on an average day. Now air pressure can change with the weather a little bit, goes up and down, but on an average day, the pressure is a certain value, and that happens to be what we call 1 atmosphere. So if we go to a higher altitude, would probably be less than an atmosphere. If we went below sea level, like in the Dead Sea Depression, then the pressure would be probably less than 1 atmosphere. So atmospheres can measure pressure. Pascals can measure pressure. They're just 2 different ways to measure pressure. In fact, there's a number of different ways to measure pressure. All right. Now, how do we measure pressure? Well, probably the simplest way would be with some water. Let me show you what I'm talking about. All right. Take a look here. I have a trough of some water. All right. I got some water and a test tube. All right. Now, what I'm going to do is take this test tube and submerge it and get all of the air out of the test tube. Now, if I take the test tube and I tilt it up like this and lift it up, the water stays inside of the test tube. If I lift it above the surface, then the water eventually runs out. Here's the question. Why does the water stay in the test tube? Why does the water stay in the test tube? It's because of air pressure. All right, not water pressure necessarily, but for air pressure, because air is pushing down on the surface of the water, and it's sort of holding the water up inside of the tube. All right, now up here in the top of the tube, the water's all the way to the very top of the tube. So there's a certain amount of air pressure pushing down on the top of this, and that will fluctuate day to day, but there's air pressure pushing down here, and since no air can get inside of the test tube, it pushes the water up inside the test tube. When I lift the mouth of it above, then air can get in there and the water all just strains out. All right, so it's air pressure that actually holds that water up inside of the tube. Now, question, how strong is air pressure? How tall could it do it? Here's a graduated cylinder. We're going to use this in the lab a little bit later. But even this one it's taller. But if I tilt it up like this, I can get air to hold the water all the way to the top of the tube. Now, is there a limit to how tall this can be? Yes, because there's a limit to how much pressure is on the surface of this water, so that pressure is being transferred to the water holding it up inside of the tube. Now, right now, so if I had a taller tube, I could hold it up even further, but water that's in this tube has a certain amount of weight to it. All right, it wants to come down, and that weight is pushing down onto the, back up to the surface of this water. So if there's a certain amount of pressure on every square inch of this water that's being transferred all the way to the water inside there, that's what's holding that up. So the limit as to how tall this could be depends upon how heavy that water is and how much pressure is on the surface of this. All right, let's see how tall we can actually get this. So here's what we're looking at in this picture. We got the air pressure pushing down on the top of this, holding the water up inside of this tube. And there's a certain amount of air pressure on this. There's a certain height at which this thing can go up. Now, what if I had a much taller test tube? Like this one here is like 3 feet long. All right, I'm going to fill this with water. I can't submerge it, so I'll have to fill it up this way. So I'm going to fill it all the way to the very top. Need a little bit more water. Keep it messy here. Start all the way up, even more, to the very top until it's overflowing. All right. Now I'm going to put my finger over the top, the opening of it, and tip it upside down, and then submerge it. And when I remove my finger, the water stays all the way to the very top of the tube. It's off the screen there, but it goes all the way to the top, so no problem. We can hold it even this far. All right, but there's a certain amount of weight on this, and that's pushing down and transferring to the surface of the water. So depending upon the density of the water, there is a limit to how high this can actually go. So this picture right here in the middle is trying to illustrate how tall you could actually get. Now, if I had a tube that was, say, 34 feet tall, that's the maximum amount of water we could hold up inside of a tube. All right, here's how it works. Pushing down on the surface of the water is the air pressure. All right, it could be measured in a unit called PSI, pounds per square inch. So on an average day, there's about 14.7 pounds of pressure on every square inch, or that would be force per square inch. So on the surface of the water, and every square inch, there's 14.7 pounds pushing on it. All right, so that's our air pressure. That's just a different unit for measuring it. And that pressure is transferred in all directions, and including up into the tube. And it's down here at the bottom holding the water inside of the tube. Now, if the tube had a cross-sectional area, say, of 1 square inch, then the maximum amount of water we could hold up in that tube would be 14.7 pounds. All right, that's going to translate into 34 feet of water. So if I had a test tube that was really, really tall, that would be as high as it could get. If it were taller than that, a longer test tube, then what would be on the top? Nothing. That would just come down to that level, and in the very top there, we would have a vacuum. Now, if the air pressure went up because of weather changes, then that height will actually go up a little bit. If the air pressure comes down, the height of that will go down a little bit. So this is actually a way that you can measure air pressure by having a column of water or a tube of water like that. So the very first barometers that measure air pressure were actually based on that fact right there. Now, water has a certain amount of density, and if you had a liquid that was a lot more dense than water, for example, mercury, Hg, then the column would not have to be nearly as tall because the liquid is so much more dense. So if you used mercury instead of water for this, then you would only have to be 760 millimeters tall on an average day. All right. So you can measure pressure in a length of a column of mercury. In the very first barometers ever invented did exactly that. They used a column of mercury set up just like we had set up here with this trough of water, and the height of it could tell you what the air pressure is. So on an average day, it would be at 760 millimeters, but then it would go up and down a little bit because of the air pressure changes due to the weather. All right, it's the first barometer. So here's kind of an illustration of what this might look like. Now, we can't set up one of these because they don't let us have mercury around anymore because of the poisonous nature. But in the old days, we used to have a barometer that looked just like that here in chemistry, and it was bolted to the wall. And you had to bolt it to the wall because if you tip it over, then of course all the mercury will come out. The part that you look at is right inside of the tube here, and there's a little window that kind of looks in on that level of mercury on the top, which goes up and down a little bit on a daily basis based on the air pressure. So atmospheric pressure is pushing down on the surface of the liquid, holding the liquid up inside of the tube to a certain height, and then however tall that is measures air pressure. So on an average day, it's at 760 millimeters tall or 29.92 inches tall, and that's just a way that we measure pressure. Even to this day, we still measure pressure in inches of mercury or millimeters of mercury. And for weather people, this is the device that they use. They look at this and they watch if it's going up or if it's going down, and that can tell you something about the weather. Rising pressures tell you that the weather is probably going to get good. Falling pressures tell you that it might be getting bad. Storms might be rolling in. Now, there's other ways that you could do this too besides this column of mercury. In fact, nowadays most people would probably use what's called an aneroid barometer, like this. It's a little container that can get squished like an accordion. And then hooked to it is this like little lever, and as that thing squishes with the air pressure changes or stretches out, then this little needle goes up and down. And then that can tell you what the air pressure is. No mercury required, and that's probably how you would do it nowadays. All right. In fact, here's a very typical barometer. It's just got one of these things, cased inside of the whole thing, and as it goes, pressure goes up and down the needle, kind of goes back and forth like that. This right here is a picture of the old school one that used to have a little lever with the ink on the end of it. And as this drum turned really slowly, like about a centimeter per day, then it would draw a line. And that line then would stretch out and go up and down and up and down. Because pressure doesn't really change a whole lot every day. But you can see it would record where the pressure was on a daily basis. You can kind of see if the pressure is going up or the pressure is going down and tell you something about the weather. Some of you maybe have used one of these, a pressure gauge for measuring the air pressure, say, inside of a tire, on a car tire or a bike tire or something like that. Now, this is measuring what's called gauge pressure, which is different than atmospheric pressure, because if you have a car tire or a bike tire and it's not even on the bike or the car yet, then on the inside the air is exactly the same as on the outside, and there's really no difference in pressure. So when you put the car tire on the rim or the wheel and then you pump it up, you're making the pressure inside greater than the pressure outside. And that's what the low gauge thing then measures. It measures the difference in pressure on the outside to the inside. And then you can measure, how much air that you put in your tire. And you want them to be at a certain air pressure on the inside relative to the outside. And we call it gauge pressure because it really only measures the temperature above or below what's on the outside. A pressure gauge, different than a barometer, which just kind of measures atmospheric pressure. All right, so we could measure pressure in lots of different units. For example, if we had the old school barometer with mercury, we could measure it in millimeters of mercury. Or we could have it in inches of mercury, or anything else that measures height for that matter. And that's a way to measure pressure in the height of a mercury column. So when we measure it this way, we usually will say something like 760 millimeters mercury. Now, millimeters doesn't really measure pressure, but in the case of a barometer like this, we can use a length to measure pressure. And it only is in reference to a barometer that has mercury in it. Now, if we had water in there, that would be a whole different matter. It would be 34 feet, and not very convenient because that's just way too tall. But a barometer that's only 760 millimeters, that's easy enough to move around. Now, if we translate into that newtons per meter squared, then we get what's called a Pascal. But in chemistry, it's more common to use kilopascal. All right, remember that it takes 1,000 Pascal to make a kilopascal. So if we translate any one of these into kPa, then we're talking about 101.325. So average pressure on an average day at sea level would be right around 101 kPa, kilopascal. It's just a different way to measure pressure. All right, and it's probably the more common way in chemistry and physics to use kilopascal. We could also then use that unit called the atmosphere, and at sea level on an average day, the pressure is 1 atmosphere. But that can go up a little bit from the weather and down a little bit from the weather and up and down based on your altitude as well. All right, so measuring in atmospheres is just another way to do it. People that go scuba diving measure the pressure of the air in their tanks in atmospheres. So if you had like 2 or 3 atmospheres, that would be, air inside your tank at a higher pressure than the pressure on the outside. Or we could use that unit called PSI, pounds per square inch. So instead of newtons in square meters, we can have pounds in square inches. So this pressure, 14.7 pounds per square inch, or PSI, is just another way to measure pressure. So all of these are the same pressure. They're the same pressure, just measured in different units. All right, kind of like you can measure length in either centimeters or inches. And the number you get, of course, is going to be completely different. So the same case here. All right, there's a few other ones too as well. Sometimes we refer to millimeters of mercury as torr. So torr and millimeters of mercury are exactly the same thing. It's just a different way to denote that. And that's named after Evangelista Torricelli, the person who actually invented the barometer there. So in his honor, we sometimes refer to millimeters of mercury as torr instead, but just a different way to do it. And he was the one that invented the device. So this list of various pressures is known as what we call standard pressure. What does that mean? That just means the average pressure on any given day at sea level would probably be close to this. All right, so that's kind of just sort of a reference point. for us. So if air pressure goes above and below it, then we can do that to like measure the weather and things like that. So these particular pressures right here are all the same pressure in different units, and we're going to call these pressures standard pressure. We have a similar thing with temperature called standard temperature, and that's just going to mean 0 degrees Celsius. So if we say standard temperature, it's just kind of a reference point, really, is all it is. And we can go above and below it too as well. So when we say standard temperature and pressure, this is what we mean, one of these pressures. So depending upon what unit you're talking about, these would be what your values are. All right, this will be something we're going to give you as a reference chart, but you have to be able to convert from one to the other. All right, let's do a few examples. For this, you'd probably need a calculator too as well. So here's how this would look. Let's say we want to convert millimeters of mercury into kPa. All right, all of these pressures right here are equal to each other. So what we could do is set up a conversion here. Now, how would this look? If I have 635 millimeters mercury, what I want to do is multiply it times a conversion factor, which is a fraction. And what I want to do is convert millimeters into kPa. So what I'll do is put millimeters of mercury on the bottom and kPa on the top. And the numbers I'll put in there come off of this chart. So for millimeters mercury, I would put 760. And for kPa, kilopascal, I'm going to put 101.325. Because these two things are equal to each other. So it's really just kind of like multiplying times 1. But we end up changing our units. So the millimeters mercury here are going to cancel out because they get some up and some down. And then the kPa is left over. So in the calculator, I'm going to punch this in as 635 times 101.325 divided by 760. So let me do this on my calculator here quick. 635 times 101.325 divided by 760 is 84.7. So I would say 84.7. We'll just round to one decimal place for now. All right, so that's what you do to convert from one unit to another. So we can have pressure measured in any kind of unit, and we might want to convert them, and we'll see when we do Boyle's law and gas laws and stuff that we have to do that sometimes. We call this dimensional analysis, or the factor label method, and it's very useful to be able to know how to set these kind of things up, and we do this sort of thing a lot in chemistry. So understanding what I'm doing here is kind of a very important piece. All right, let's try another one. Number 2, I've got 0.851 atmospheres, ATM. All right, so I need a conversion factor. And on the top, I want my millimeters of mercury. And on the bottom, I want my atmospheres, so that my atmospheres can cancel. All right, what will I put in there? I'm going to put a 1 for atmosphere, and I'm going to put 760 millimeters of mercury. So then I multiply 0.851 times 760 divided by 1, and that will convert. So 0.851 times 760 divided by 1, which I don't really have to type in. If I do, not a problem. 646.8. I'm going to go with 646.8. So 0.851 atmospheres is 646.8 millimeters of mercury. All right, always kind of important to put the mercury in there too as well. All right, let's try another one. 65 psi, that stands for pounds per square inch. And I want conversion factor with pounds per square inch in the bottom and millimeters of mercury on the top. And I'm going to put 14.7 on the bottom and 760 on the top, and then multiply 65 times 760 divided by 14.7, and I get 3,360. 3,360 millimeters of mercury. So that's a large pressure, much bigger than atmospheric pressure. That would be like, a pressure tank of gas for scuba diving or something like that. All right, let's try the last couple here. 421.5 kPa, kilopascal. On the bottom I want kPa. On the top I want atmospheres. And on the top will be 1, and on the bottom will be 101.325. So 421.5 times 1 divided by 101.325 is 4.16. 4.16. 755 millimeters of mercury. And I want to convert that to kPa. And on the bottom I'll need millimeters of mercury. So that'll be 760 and 101.325. 755 times 101.325 divided by 760. 100.7. 100.7. All right, so that's how we convert from any one of these pressure units to any other pressure unit like that. And in fact, these different units get used quite often in different places. In chemistry, most often we're using kPa for calculations and stuff, but in the United States, you're measuring things in PSI, like your tire pressure, and you're measuring probably in millimeters of mercury or inches of mercury. Most weather people use inches of mercury to kind of denote the air pressure on any given day. Watch the weather. Nowadays they don't report the pressure too much because not that many people really know anything about it. So, but you still, if you Google weather, that's going to probably tell you something about the air pressure. Rising pressures means good weather's coming. Falling pressures mean that bad weather's coming. Generally, that's not always exactly right. But all right, that was a lot of stuff. So thanks for watching. Next thing we're going to do is on Boyle's Law, which relates pressure and volume for a gas.